Talk is on a group of rational points of simple algebraic groups. This is my first lecture here, first talk here, and this is how I begin. I'm really sorry. So I divide my talk roughly in four parts. The uh, first part is on what are called central simple algebras, and it connects to a group theoretic problem called Tannaka-Artin problem. So there is so this Tanaka, sometimes the spelling is what with a single N and here it's double N. So that also is maybe a mistake. I don't know. It's a Japanese name. The second part I would like to call isotropic simple algebraic groups and the Kneser-Tits problem. The third part is a slightly geometric in nature called rationality of group varieties and something like path connectedness there it's called R equivalence in algebraic groups. One can talk about R equivalence in general, but I am interested only for algebraic groups. And in the end, if I have time, I will mention some recent results. So I begin. The first part is central simple algebras. So these are algebras which, when you go all the way to the algebraic closure, becomes a matrix algebra. So A tensor k bar is mn k bar. We call this n as the degree of A. So one example which I did not write here, for example, if you take the quaternion division algebra over reals, so it's not a priori a matrix algebra because it's a division algebra, right? But if you base change to the complex numbers, you get 2 by 2 matrices with complex entries. So the degree of quaternion algebra is 2, dimension is 4. So square root of dimension is called the degree. Dimension is always a square because of what I said. And then there is a well-known classical theorem of Wedderburn. It says that any such algebra is a matrix algebra with entries in a division algebra whose center is exactly equal to k. So such things are called central division algebras. Please feel free to ask doubts and stop me wherever you can. This is supposed to be an expository lecture. And again, I feel very bad for starting like this, but sometimes life is like that. So now let's look at this A tensor K bar. It contains A as a K subalgebra. So I can follow any element here by a fixed isomorphism to think of it as a matrix and take its determinant. So that map is called the reduced norm map of A. And because determinant is multiplicative, this map also is multiplicative. And same again, because of determinant properties, we actually get a group homomorphism from the group of units to invertible scalars in K. So this requires a little work. A priori, the determinant of A tensor 1 will be an element of K bar, but actually one proves with basic technology that in fact it's a scalar in K. So you have a group homomorphism. The reduced norm map uses a group homomorphism from the group of units in A to the group of units in K. And SL1 of A is a notation for the kernel of this homomorphism. In other words, the set of or the group of all norm 1, I'll just call it norm now on, all norm 1 elements in A. And this is the commutator subgroup of the group of units of A. Since the reduced norm map is multiplicative, it's immediate that any commutator is norm 1 element. Therefore, this whole subgroup of A star becomes a subgroup of SL1 of A. Actually, again, I am a little confused about Tannaka-Artin. I think it was a conjecture, not just a problem. So the conjecture was that this quotient is trivial. In other words, every norm 1 element can be written as product of commutators. That was the conjecture. Uh, let's denote it here as sk1 of A, this quotient. which by definition is SL1A modulo the commutator of A star. And one knows, uh, if you look at the Wedderburn theorem, it says it is of the type MR of D for a division algebra D. So one knows this isomorphism using Dieudonné determinant, which I won't go into, that SL1A modulo the commutator of A star is isomorphic to actually SL1D modulo the commutator of D star. And that is SK1D by this notation. The first result was due to Nakayama and Matsushima in this. They proved that over periodics, indeed, for any central simple algebra, SK1 vanishes. And Wang in 1950 proved this for number fields. No condition on A. Any central simple algebra, SK1 vanishes over number fields. This is a result of Wang. Moreover, he proved that SK1 also vanishes for any central simple algebra over a field K, as long as the degree is product of distinct primes. So this was pretty old result. In 1969, Platonov proved this for general local fields, and also he came up with counter examples. Hello, can you hear me? Hello?
Yes, we can hear.
Okay. I'm sorry to ask this
Yes, Maneesh,
question
it's fine.
because you
Yes.
see, already we have failed video and audio both. So I will keep asking you again and again. So
Fine, we
yeah.
can hear you.
So Platonov gave this counter example to vanishing, in fact, and this, for example, if you take power series, the field of Laurent series in two variables over rational numbers, their tensor product of two quaternion division algebras provides an example. So I will not go into this, but this example, maybe one would take another talk to describe this. But Platonov came up with this counter example in 1969 and also started developing at that time till as long as 1976 what is called reduced K theory of division algebras with some other mathematicians also involved. So this is so in a way, if you want to, since the workshop is called Sangam of, I called it Sangam of group theory rather than Sangam of group theorists. So there are three things here. One is coming from K theory, algebraic K theory. And then, of course, algebra should, if one calls study of algebras as algebra, then you have algebra also here, and you have group theory also here. So this is group theory, algebraic group theory. So we have Sangam of three streams here. So let's proceed with that. So the second part, I wanted to talk about isotropic simple algebraic groups and the Kneser-Tits problem. So I told you already, beware of mistakes, and there are experts in the audience, they will catch me. So I will already say that I was in a hurry, and so don't mind. So let's take a division algebra over a field K and look at the algebra of n by n matrices with entries in D. And let's assume n is bigger than 1. Okay, that's important. I'll tell you why in a minute. Then SK1 of A is trivial, is equivalent to something purely group theoretic statement here, which is the group of norm 1 elements in A quotiented out by its center. This should be a simple abstract group as we know. Okay, this again is equivalent to the statement that, or the assertion that SLND, so which is same as SL1 of A, this is generated by what are called unipotent matrices. So unipotent matrices you can think of as these are the prototypical unipotent matrix. So once on the diagonal and a non-zero entry anywhere else you like, and you conjugate it around, you essentially get all of them. So these statements are equivalent. Okay, so any questions so far? Uh, Please stop me whenever you feel like. So next, I wanted to get into slight algebraic group theory. So for me, I will define a linear algebraic group as just Zariski closed subgroup of some GLN with entries in K bar. And we say this is defined over K if the defining equations can be chosen over K. Okay, and call G to be simple over K. So remember, this is now an algebraic group. This is not just no more an abstract group. It has some extra structure of an algebraic variety. So the notions are slightly different here. So we discard, so we just say simple if it has no connected normal, non-trivial subgroups other than itself. That is the notion of simplicity here. For example, you can look at SLN, SON, SPN, SLND. These are all examples of simple algebraic groups. So I did not tell you what SLND as an algebraic group is, but let's go ahead with this. This is more or less correct. And their group of K rational points. So what does this mean? K rational points means, so these groups are defined by certain polynomial equations. You are just looking at solutions which live over K. So that is a group, abstract group, that is called the group of K rational points of these algebraic groups. So other than this SL and D, this is a mistake here. Forget this as for the last assertion. If you mod out by the center of these group of K rational points, you get something projectively simple. That means you get a simple group. So any of these groups, modulo their centers, SLNK, SONK or SPNK, modulo center, that's an abstract simple group. Okay. So group theory is interested in looking for simple groups. So these are already well-known simple groups. Here I said I assume K is perfect, and this definition I make is actually not correct. But let me say this anyway. So what is incorrect there? So let's assume K is perfect for some other reason, just to be careful. Here I say G, simple algebraic group, I call it isotropic over K. Here I say if GK contains a non-trivial unipotent element. This works only in characteristic 0. Characteristic P, where P is not 0, this is false. One can write down simple examples where this doesn't hold true. So let's anyway brush it aside. Right now, I'm not bothered about that. So I told you what is correct. The correct way to define isotropic groups is using tori, which I wanted to avoid, or parabolic subgroups. But this is for the moment, let's keep in mind characteristic 0 if you want to be correct. So for example, G, SL and D, when n is bigger than 1, is isotropic over K. So we saw plenty of unipotents there, and by any definition, these are isotropic groups. And if you fix a non-degenerate quadratic form over K and look at the group of spatial orthogonal group, for example, or even the orthogonal group, then it is isotropic over K is equivalent to saying it has a non-trivial 0 defined over K. This is a simple exercise, a beautiful exercise you should try if you are interested. And also you can write down, you assume Q has a non-trivial 0, then you can write down by hand the unipotent generators of this, unipotent elements in this group using one vector which is isotropic, which means 0 of Q. So let's call by GK plus the subgroup of GK generated by unipotent elements in GK. So remember, G is an algebraic group, so it is, you should think of it as a subgroup of some GLN. So you can think of elements of G as matrices. So you can talk of unipotents and so on living inside the group of K rational points. Take the subgroup generated by that. That is what we are calling as GK dagger. And clearly, if a matrix has all eigenvalues equal to 1, then any conjugate of that also has the same property. So this will be a normal subgroup of GK. One more notion I need to define is of simply connected, roughly speaking here. So let's take a simple group G. We call it simply connected. If I have no connected group G dash, uh, or given any connected G dash and a surjective morphism with a finite kernel, then that morphism is an isomorphism. So this is the notion of covering there, surjective homomorphism with finite kernel. So any such homomorphism becomes an isomorphism, then you call G simply connected. Is it okay so far? Uh, People around or have gone for tea?
Yes,
Okay.
yes, it's fine.
So let me come to Kneser-Tits conjecture. This was formulated in 1963 with the evidence coming from the field of real numbers, finite fields, PRDICs, or whatever little one knew till then for what are called global fields. This conjecture was that if I have a simply connected and isotropic group, remember, isotropy is particular to the field. A group may very well be unisotropic over K, but if you go to an extension, it becomes so. Just like finding zeros of polynomials, right? A polynomial may not have roots over the field, but if you go to some extension, you find roots. Similarly, isotropy is something like that. So if you have a group which is simple, simply connected and K isotropic, then the conjecture says that GK equals GK dagger, which simply means GK is generated by all the unipotents. This was expected, but Platano, we saw, so Platano in 1969 proved this conjecture for local fields, and there was some Indian contribution more than this. I will come to this. Prasad and Raghunathan, they reduced this to proving the assertion for all rank 1 subgroups, for all rank 1 groups. I'm sorry. And Platono's produced counter example for groups of type AL. These are the groups which are, this is a group of type whatever. I don't want to say what L because I did not specify what D is. But these are the groups essentially for which there are counter examples. These are the, in a way simplest in algebraic group theory, but there itself there is counter example. So people hadn't explored all kinds of fields, but whatever data was available from that, it seemed correct and the conjecture was formulated. However, it was false. So Platonov's counterexample certainly disproved the conjecture, but it started some new branch of mathematics. And this quotient for SLN D turns out to be exactly SK1 of D. So Platonov proved SK1 or constructed D where SK1D is non-trivial. So there is a takeaway result for group theorist here. So remember, algebraic group is simple. The definition is a bit tricky because you just want to talk about connected normal subgroups. You don't, for example, SLN, you allow to be simple even though it has finite centers. So you forget that. You should look at only connected normal subgroups. They shouldn't exist. So let's take a simple, simply connected and isotropic group. Then Tits proved in 1960 that this subgroup generated by unipotents is a perfect group and is projectively simple. So as an abstract, so you get lots of, you can just write down lots of simple, simply connected isotropic algebraic groups, and this tells you a machine to produce infinite simple groups if you like. So this is one result which you can take home from this talk. Of course, there are these technicalities. Oh, I didn't know there are such young participants for my lecture. Good, good. One should catch them young. So the third part of my talk is somewhat geometric in nature. So we define uh, R equivalence in this section. Rationality is the property I have in mind. So we call an algebraic group rational if its variety is like an affine space. So not exactly isomorphic to an affine space, but there are open sets here and there which are isomorphic. For example, here I have made a mistake again. So SOQ is, in fact, this is correct, is birational to its Lie algebra. And this, what I have written, is true for SON. So here the same little modification will give you a proof for SOQ also. So this is a rational group. And what are called split algebraic groups, they are rational. So SLN, for example, is a rational group. Simple algebraic groups of type of rank at most 2. So rank is something I have not defined. So what is rank? So in all these algebraic groups, you can find a diagonalizable subgroup, even if it may be trivial. So by diagonalizable, I mean you can, just like matrices, you can conjugate and diagonalize them whenever they are diagonalizable, of course. You can't force them to be diagonal. But if they are diagonalizable, you can diagonalize them over some field extension. But so let's go all the way to the algebraic closure and look for connected subgroups whose elements can be simultaneously diagonalized. Okay. And this number denotes the dimension of that subgroup. So any algebraic group has such subgroups. They are called maximal tori, the largest ones, and rank is the dimension of such a torus. So here we are saying that any algebraic group in which maximal torus has dimension at most 2 is automatically rational. So this is a theorem of Chevalier, very old theorem. And Platonov's result connects to this, that a central division algebra D over K, then SL1D, which we know need not be rational. This is rational implies SK1D is trivial. So the moment you produce a counter example, so if non-vanishing of SK1D implies that SL1D is not rational. So this is a bit too strong a notion for algebraic group theory. One can do with a little less. So let's consider now this notion of R equivalence. So let's take connected G. Take two k rational points x and y in G. Let's call them R equivalent. If I can find a rational morphism from the affine line to G, which is defined over K and regular at 2 points 0 and 1, such that at 0 I have X and at 1 I have Y. So you can think of this as some kind of path joining X and Y within the group of K points. So let's take R to be the set of all elements which can be joined to the identity element. Then one can show with some effort that this is a normal subgroup of GK. And look at the quotient group. The quotient group is in bijection with the group of this is an equivalence relation, so you'll get set of equivalence classes that is in a natural bijection with this quotient group. So one can think of the group of one can talk of the group of R equivalent points of G. And but by what we saw, if G is rational, then just everything can be joined to the identity. So GK mod R would be the trivial group. And also if rank is at most 2, then already G is rational, therefore this will be trivial. This actually, I will use this later if I have time to sketch. Well, I don't have time to tell you proof of anything, but so let's proceed. So one definition, we say G is R trivial. So G is a connected algebraic group. I can make this definition for anything. G is R trivial if for all field extensions, nothing specified here, L over K, GL makes sense over that because G is defined over K, so GL makes sense. That modulo R should be trivial. So this is the definition of R triviality of groups, which is rather strong. And we saw, one can say that, see that GK dagger is contained in R. So we saw this in example of SLN. Actually, one needs to work. It's not so trivial, but if you look at SLNK, there you can see easily. You can just connect any unipotent to identity matrix by means of a straight line segment, in fact. So, but in general, this is true. This is always contained in R. This R means these are the points which can be joined to the identity by a rational map from affine line. In 2000, Philip Gill proved in general, in fact, so this was the result proved by Platonov for SLND. So in general, it was proved by Philip Gill that, sorry, did I say Platano? I may be wrong here. Maybe this is due to Voskresenski or something. I'm sorry about this credit. It may be for SLND, this perhaps is due to Voskresenski. Anyway, doesn't matter. So G is simply connected, K simple and isotropic. Then GK mod GK plus is actually isomorphic to the group of R equivalent points of GK. This is in 2000. So triviality of Whitehead group. This is called the Whitehead group. This group. This is equivalent to triviality of GK mod R. So one interesting thing here is the right hand side here. This makes sense for any algebraic group. However, to make sense of this quotient, we need unipotents in the group. So this quotient is more general. One can, so there are conjectures on this quotient. One can work on those. Still, one expects this group, for example, to be always abelian. This is not proved till now. All the examples one knows it turns out to be abelian, but it's an open problem. Yeah. So let me. So I seem to have gone rather faster than what I imagined. So let me come to the last section now on recent results. This is on Kneser-Tits problem. So here I should mention one result of Raghunathan which I couldn't find published anywhere. And I had met him at IIT Bombay and I had a very soiled preprint of his, which I found as a student in TIFR somewhere lying around in committee room and I had picked it up. I never knew that I'll study it someday. So it's called, the preprint is called A Note on the Kneser-Tits Conjecture for Global Fields. And it is only by Raghunathan. It's not Prasad and Raghunathan. And here he proves that if F is a global field and either G is a classical group or the rank, so F rank, so there is something called the rank over the base field. I will not get into that. If F rank of G is at least 2, then this Whitehead group is finite and abelian. This is Raghunathan's paper here, which I don't think it was ever published. I think those days are gone when people used to prove theorems like that and not publish. Now everything is published. Okay, so that is Raghunathan's paper, and I couldn't find when it was published. So recent results. So one knows now that over global fields, Kneser-Tits conjecture holds for all groups. Recently, certain gap was filled, which was the trilitarian D4 case by uh, Gopal Prasad and Raghunathan's old result, but it was written up in a different way by Gopal Prasad. It's a new paper. So, and yeah, so let me go to what is the latest on this. So coming to exceptional groups. So classical groups one understands pretty well, and what is not trivial there leads to K-theoretic objects. So I will not go more into K theory and so on. But exceptional groups, the situation is completely ill understood still on in many senses. So let's begin with the smallest one here, this G2. These numbers, lower numbers, indicate what I call the rank. So these are the ranks of these groups, which is the dimension of largest diagonalizable connected subgroup. So G2 has rank 2 and therefore it is rational, and I told you that any rational group is R trivial, and anything R trivial then white-hat group vanishes and so on. So this is completely understood. So there it's Kneser-Tits holds any version of G2. F4 rationality properties are pretty ill understood. However, there are some R-triviality theorems for F4 due to myself. And independently, there is a trio which has come about together recently of Al-Saudi, Chernosov, and Pianzola. So we independently prove the same theorem. I proved one more after them, but anyway, this is the story. And there were some Kneser-Tits conjecture was recently proved for some groups of type E6, E7, and E8. E6 was by Garibaldi, E7 and E8 again, I will come to this. But the technique was using R triviality of what are called anisotropic kernels. So there isotropy is not necessary. To prove R triviality, you can do it for any group. The notion makes sense in general. So this is a version of, this is the largest algebraic group, simple algebraic group. This denotes the K rank, and this is the dimension of the anisotropic kernel. This conjecture was settled for this version of E8 by Parimala, Tinol, and Weiss in, I think, yeah, maybe 2011 or some such, I forget the year, but yeah, somewhere around that, or 12 maybe. And then comes the other version of E8, which is again rank 2. Rank, of course, E8 is rank 8, but this is K rank 2. And anisotropic kernel is 78 here. It's a group of type E6, in fact, anisotropic E6. And this sits here as a subgroup. This is a version of E7 of rank 1 and same anisotropic kernel. And this Kneser-Tits was proved by 3 people, the same trio there, and independently by myself. So these are very recent results. I am, in fact, I just now got a revision request for that paper, so it is still not yet published, and I don't know about their story. But interestingly, yeah. So this is all I wanted to say about these results. I'll be very happy to explain anything you want, and I again apologize for the goof ups initially. I am glad Anupam could do something. Amit, very much thank you for this amazing technological success. Yeah, so I stop here.
Hello, are there any questions or comments? The time for interaction.
Maneesh, can you explain this last bit a little bit?
Yeah, which
like
part?
about this forms or ranks E8 thing. What does it mean? I mean, the
Oh yeah.
symbols.
So unfortunately,
For
I'm
general.
handicapped technologically. I don't have anything to write on here so far. But so I can explain what this. What do you want me to? The notation, huh?
Yeah, in some
Okay.
sense.
So
Okay.
E8 is a simple algebraic group as large as one gets. So think of it as as the largest simple algebraic group possible. So that is E8. The 8 denotes dimension of largest torus inside that. So that is 8 dimensional. And 2 here denotes the torus. So see, over algebraic closure, the torus has dimension. You will get a diagonal subgroup of dimension 8. But over the base field, you may not be able to find that. But here I want the version where the base field has 2-dimensional torus there. So this is 2 copies of multiplicative group of the field. So just like think of like SL1 of a quaternion algebra versus SL2 of complex numbers. So SL1 of quaternion algebra has no copy of any split torus there, but SL2C has a one-dimensional torus. Similarly here, so this 2 denotes over the base field, I have a split torus of dimension 2. I didn't get into the definition of what split means, but I haven't even defined GM, unfortunately, thanks to everything. And this number, so these two numbers are clear, I explained.
Right.
Well, I cannot do more than that, perhaps. So those who know, this 2 denotes the dimension of K-split, maximal K-split torus. And this is the absolute rank. So you will see this over K bar. And this 66 denotes what is called, so this is dimension of a certain subgroup here called the anisotropic kernel of this group. So that is, again, think of it in a very incorrect way, perhaps the largest anisotropic part of the group. So isotropic, I explained, anisotropic is the other extreme. So that has dimension 66. I should have drawn pictures, here I didn't draw pictures because then I have to explain pictures also. So there is a picture here, this is D, what? D12 or D14 something. I'm using the notation DN. So I think 14, right? What is, no, 12 into 11. Yeah, it's D12. So this is SO of 24. Am I correct, Anupam?
Yeah, that looks correct.
Yeah, so this is SO of 24. Okay, so think of orthogonal group of a 24-dimensional quadratic form, anisotropic quadratic form. That is a subgroup here that has dimension 66.
Sorry, maybe you mean D6? SO12.
SO, you're right. D6, sorry.
D6 can sit in A8, but meaning putting D24 inside or
Yes,
D12 in E8 will be difficult.
good. Shripad is around, so I don't have to worry. Yeah, so this is D6. So SO12 sits here as an isotropic kernel. And here, this is more complex. So if you saw a picture of E8, then it has a nice symmetry. Well, not really. There is no symmetry there. But these are the end vertices are circled. So if you omit those 2 vertices, so again, the split torus has rank 2, maximal K split torus. You omit those vertices, then you get a copy of E6, and that is the anisotropic kernel here. Same thing for E7-1. Here the K split torus has dimension 1. And so you omit that circled node, then you get E7, E6 again, and both anisotropic kernels are same here. So this guy sits there, in fact. Yeah, so I wish I had been more careful and pretty on my notes, but and also a lot of inaccuracies in my notes. I apologize for that. But Corona, I blame everything on coronavirus. So any more questions? I'll be happy to answer.
I have a basic question, Manish, but
Yeah.
somebody else has it. Go ahead. Someone else was asking.
Yeah, so I wanted to ask you a question.
Yeah.
Can you hear me, Maneesh?
I can't see who the person is asking. I have no idea. But anyway, yeah.
This is
That should be Pralay.
My name is
Question.
Pralay.
I can't hear the question.
Yeah, the question is, can you recall this Philip Gill's result?
Oh, Jill's result was, yeah. So GK mod GK dagger is isomorphic to GK mod R. Don't ask me the proof right now.
No, I'm not asking. So does he prove that R is same as GK plus or?
Yes, more or less, yeah. More or less.
So
not really. I'm saying more or less. Don't be careful.
So the question is, so you seem to have written some isotropic conditions. So can I say that this R is trivial if the group is anisotropic?
No. R is
That's not
trivial.
right.
Oh,
So
this
you need
right-hand
to
side.
assume R.
What are you talking about? This right-hand side?
No. I'm saying that Philip Gill proves that R is GK plus, right?
No. I don't think so.
Okay.
No.
So
That's
what happens if the group is anisotropic? What can you say about R?
nothing can be said in general, but we saw already the example of SL1D. So
Okay.
that R can be SL1D. If you look at G equal to SL1D, then there this the quotient is no. What am I talking about? So yeah, so you can't say much actually.
So, I mean, this side is very clear, right? I mean, GK plus should be inside R. Is that it should be clear, right?
Yeah, but this anisotropic groups, this is not understood. This quotient is not really understood in
So you
general.
need to really put that condition. It is not. I cannot just say that G is simply connected and K simple. Then GK by GK plus is GK by R. In that case, GK plus will be trivial in case of anisotropic.
Yeah. So if G is anisotropic, then GK plus is trivial. But so this for this theorem we need isotropy, of course.
Acha. Okay.
Yeah.
So this is
This is very strongly used. Otherwise, this whole thing doesn't make sense. Yeah, to make sense of the left hand side, to any degree, one should assume G is isotropic, simply connected and so on.
okay. But the R makes sense over anisotropic group. So that is also
R
not
makes sense for any connected group. Yeah.
okay. Okay. Thanks, Maneesh.
No, but this thing is still very ill understood. Conjecturally, this is an abelian group. As you can see, you will be able to see that. Not you cannot see the proof, but it makes sense to ask that question: is it always abelian?
Yeah. Okay. Thanks.
Okay, so I can now ask. So I have two basic questions. Number one, since we have Philip Gill's result on the slide already, is there any condition on the field K, or it's a general field?
No, this is general.
This is general. Okay.
Yeah.
And second question again at towards the end, the various isotropic groups of type E7 and E8.
Yeah.
So here we just write those numbers of as the dimensions of the anisotropic kernels. But are these groups possibly unique, or there can be many groups of this type?
No, there
Meaning
are many group. No. So these are types.
these are only types.
The wrong thing as I already owned up did was I did not draw diagrams. So it's like saying, given a Dinkin diagram, is there a unique group? No, there are many groups over the base field. I mean, so base field has these what you may call as avatars.
Correct. No, but what my question was that if we write just E8, and if we understand it being a split group, then there is a unique group.
Yes.
So here you are talking about the rank being 8, the K rank being 2, the dimension of the anisotropic kernel being 66. But even then, there could be several groups of type D6 which may come as anisotropic
So
kernel.
let me clarify here. For example, this is parameterized by those quadratic forms which have I may be wrong here, trivial discriminant and some other trivial invariant. So the moment you have one such quadratic form, you will get a form of this type, a group of this type. Change that quadratic form, you get another one. Similarly here, these groups are parameterized by what are called Albert algebras. So you pick an Albert algebra, then you can write down the group. But you can change the Albert algebra, then you get a different group, as long as those Albert algebras are not isotopic. Okay. So these Albert algebra, so the theorem is that these groups exist over the field as long as you can find a degree 3 division algebra whose reduced norm map is not surjective, or an division algebra with involution of second kind whose reduced norm map is not surjective. Then you can write down these groups immediately. Many of them. So
Okay. Yeah. Thank you.
Are there
here there are 3 authors and they did it at one go. This is my third paper on the subject, and I wrote alone. So there is some symmetry here.
Triality.
Yeah, sort of.
So if there are no more questions, let us thank Professor Maneesh Thakur for a wonderful talk. Although it was a little late, but he did a very good job.
Thank you, Maneesh.
So do I leave the meeting or?
If you want, you can stay. We are here for discussions, further discussions.
We
More
normally
minutes to
chat
talk
for
to
5-10
people who
minutes.
are want to talk to us.
So I will
You can
send
stop sharing.
You can stop sharing. Yeah, that's.
So I will send this to you later.
You send it to Anupam. And
Yeah.
Yes, yeah.